Hello, everyone. Welcome to our Citrus People in Robotics seminar. And we're delighted to have as our esteemed guest here, a good friend and a colleague who I've known for many years. In fact, we're brothers. We have the same advisor, so that's what that means. We both had the great fortune to be advised by Matt Mason at Carnegie Mellon. Now, Alberto has a fascinating history. He actually comes from Spain. He was at the University of Politècnica de Catalunya, and he has a degree in math and telecommunications engineering. Right? Okay, good. And then he came to Carnegie Mellon, and he worked with Matt on a number of problems in manipulation, which as Matt has said, he's been working on the same problem for 40 years or something like that. I've only been working on the same problem for 30 years, but we still haven't figured it out. But with guys like Alberto, we're on the right track. Alberto made a number of interesting contributions. He's done a lot of work in caging, which is something I don't know if you'll talk about today, but it's another topic, but very interesting in regard to grasping. And then in regard to grasp control, he's written a number of interesting papers, and then moved to MIT, where he was also working in the locomotion lab. Then he's was hired as professor there. He has won a number of awards. He's gotten Best Student Paper awards, and he is now the Walter Henry Gale Career Development Professor in the ME department at MIT. And I should also mention the winner of the Amazon Robotics Picking Challenge this year. So we're super proud of him, and we're lucky to have you here. So please welcome Alberto Rodriguez.
No problem. Thank you. Thanks for the introduction and the invitation to give a talk. It's a pleasure. So today I'm going to talk a little bit about the you know how this works, right? So I really want to talk about the work that I do, right? How great it is. But first I'm going to try to motivate a little bit why we're working on grasping, or why we're working on identifying what are the things that are still not solved about grasping, or why grasping is not a solved problem. So this is a story that starts with great expectations, right? So this is the last slide that I used for my faculty talk 3 years ago. You know, you need cool stuff, right? Fancy stuff. You need to think about the future. It would be useless to get a robot to do this kind of thing, but the technologies that are necessary to get the robot to do these kind of things would be very useful, right? Why great expectations? Because this is very far into the future. Robots are not nearly anywhere where they could manipulate an object in their hands with this amount of dexterity. So the story of the manipulation problem is a story that starts with great expectations, but has diminishing expectations, right? So manipulation is a very broad problem, right? You're putting on your jacket, or juggling, or playing with clay. That is manipulation, right? But I don't even know how to represent that problem. I don't even know what it means to, what is an action when I'm putting on or taking out my jacket. So we've been sequentially looking at problems that are a bit more constrained or a bit more structured until we find a problem that we can attack, right? So this is just a handmade representation of what I call the ladder of shame, right? So how gradually we're going into like this corner where we finally find a problem that we can attack. You can think of going from this broad manipulation problem to more structured manipulation, where maybe I still don't have like a good representation of the space where the world lives, but maybe I know that there are certain actions that I can take to change it, right? I can slice something, or I can glue something, or bend something. That's still like hopelessly complicated to at least understand the structure of that problem. You can go down a bit more, parameterized manipulation, where objects now live in like parameterized configuration spaces. Imagine like operating a valve, right? Or turning a key, or a screwdriver, or some sort of rigid tool that you use that moves along a certain path. Getting robots to do this, it's still a problem, right? We don't have like good ways to design policies or plans to get robots to execute motions like this or actions like this robustly. So we go down, okay, forget about using whatever you're grasping. Just think about grasping, right? So how do we get an object into the hand of the robot so that hopefully then we'll figure out what to do with it. And by grasping, I mean the entire process of approaching the object and like thinking about all the dynamic contact interactions between the hand and the environment and the object as you're closing on it. That's still something that we don't know how to model, we don't know how to simulate accurately, or we don't know how to plan for these actions, right? So let's just think about grasp, right? So I have some contacts on the object, and geometrically I can understand whether it's a good, better grasp or worse grasp. And this is a problem on where we've gotten some traction over the last 40 years, right? And all the way from geometric analysis to neural network approaches to model grasp stability, but there's still like a big work we have to do to go up the ladder so that we can tackle these useful problems, right? More complex problems. So just as a motivation to the rest of the talk, focused on this, I want to give a little bit of briefing on the work we did for on the Amazon Picking Challenge this last year to sort of illustrate, I don't know if we call it state of the art, but close to what grasping systems might be working like today. So the Amazon Robotics Challenge, unless, if in case you haven't seen it, the basic idea is you get a container filled with objects like this, and you need to design an autonomous systems to pick all these objects and identify them and then put them in storage. And you have to do it fast and reliably. So it's a challenge that has like environment obstacles, right? So things are not living in space, they're living inside the constraints, and you have to avoid them. There's clutter, you have to pick up objects like wherever they are accessible. And then there's object variability. There are objects that are, I don't know if it's rigid or non-rigid. It's clearly non-rigid, but it's also not soft, right? So there's a huge variability of objects, and you have to deal with all of those. Okay, so quickly, this is one possible solution. This is what we presented in the challenge. There's an arm and a gripper and some cameras, and then there's a control loop here. There's a computer here that is driving the entire thing. So when you want to design a system like this, when you want to design a pick-and-place system, you basically have to answer 4 questions that are completely interrelated between them, right? So the first one is a design question, right? What end effector are you going to use? What is it physically going to touch the objects that you need to pick? Are you going to use a gripper or a suction cup or a combination of both? What are going to be the degrees of freedom? In our case, we decided to use a task-based gripper design. Can you read the slides? Can you see the slides? Okay, cool. The idea is that you can incorporate some of the constraints of the task into the design of the gripper so that the task becomes simpler, right? So there's force control when it closes, and there's a spatula here that is compliant so that you can touch things safely, you can squeeze in between objects. The suction cup goes far enough forward so that the rest of the gripper is not an issue when you have to deal with collisions. Anyway, so you input task constraints into the design of the gripper. The second question is what I would call manipulation, right? So what is going to guide the design of the particular interactions between the gripper that you chose and the objects? Are you going to use some sort of contact-based planner? Are you going to think about force control? Are you going to think about the particular interactions in any given way? In our case, we decided to simplify the problem by looking just at a particular finite number of primitive behaviors, right? So we thought, okay, if the objects are going to be inside this toad, and if the objects are going to be of these particular kinds, we think we can pick them all just by looking at suction down, suction side against a face, grasp down, and then flush grasp, so where one finger gets in between a wall and an object. And each one of these behaviors has its own planner and its own controller and its own perception system, which I'll talk about in a second. The third question is, once you have a gripper and you know how that gripper is supposed to interact with the object, how are you going to use the robot to make sure that the gripper can follow that path, right? How are you going to avoid collisions? How are you going to make contact in a safe way? So you can avoid collisions by forcing the robot to move in safe zones so that you don't have to do collision-free planning, right, just for speed. Whenever after picking something, it just goes up and it goes on top of things so that you know that it's never going to collide. And we can make contact in a safe way by having guarded moves, right? So we have sensors that tell us the moment it makes contact so that you can directly react after that. And the fourth question is perception, right? So where is the object and what object that is? This is a problem where, again, standard research solutions are difficult to use, right? So the standard pipeline of segmenting an object and then identifying the pose of the object and then planning a grasp for that particular object is very noisy because it's very difficult to segment what is a toothbrush here from everything else that it just becomes clutter. So instead, we decided to use techniques that are being developed, that have been developed in the last few years based on affordance prediction for each one of the primitive behaviors, right? So we train a neural network to say that this is more likely to be suctionable than this area over here, right? And we get the neural network to predict like dense affordance maps for each one of the primitive behaviors. Okay, so maybe a bit more in detail how the system works. There are two problems we need to solve. One is like grasp selection, right? So we need to come up with these affordance maps. And the second one is object recognition. After picking the object, we need to make sure that we pick the object that we really wanted to pick, right? So this is what they No. Here, no. In my research, or in general, yes, I want to worry about that. And that's sort of what I'm going to talk a little bit later. But the idea is that sort of this is building up to say, well, we don't know how to do that. Okay. So we need to figure out which object we picked, right? So we need to make sure that we can match this image with the product images that Amazon gave us, right? So you have to remember that the system has never seen these objects before, right? The only thing that it knows about these objects are these product images and maybe the weight of the objects. So this is one particular moment in the challenge, and we get some RGBD input images to the system, right? So what the camera sees in RGB and depth, and then we pass these images through the neural networks to do affordance prediction on the things that look like are suctionable and the things that look like are graspable for different orientations of the gripper, right? So we merge the heights and then we rotate these heights and different orientations to make the prediction of these affordances for each one of the picking behaviors. And now, once the controller receives these, the idea is I just need to look at whatever is more likely to succeed, and then I go, which in this case, it looks like this is the highest point from all the options, which corresponds to this grasp, and then the robot goes down and picks it. And after that, it goes back up, and it shows it to the other cameras that do image recognition, right? It looks at this object, and it has to decide which one of the database of objects that it has is, and hopefully it makes a good prediction. This is also done with some sort of with a neural network interface where we learn a feature embedding where these kind of images, which are the product images, look like these kind of images, which are the ones that we capture in real time. Why do we do this? Why do we need to learn a feature embedding? Because we've never seen these objects in real time. The only thing we have are product images, and matching directly from here to here is quite noisy. So how do we solve that problem? We go to Target, we buy like 250 objects, and we get training data for this kind of matches. And then we learn a feature space where they look as close as possible, right? We learn a feature space where these two images map to as close as possible to the same cluster. Then in real time, we get a new object with a new real image, and hopefully they will get as close as possible in this new feature space. Okay, so I'm happy to talk more about the details. I don't have many here, but once you answer these 4 questions, which are intertwined, right? So the decision of how you're going to use the end effector affects the design of the end effector, right? And vice versa. And all these, like the perception is designed for the particular behaviors that you pick up here. And the path is influenced by what areas or surfaces of your end effector are going to make contact, right? Where are there going to be collisions that you want to avoid? But once you answer these 4 questions and you spend a couple extra months like debugging the system and improving it, then you can do runs like this. This is the official run actually of the competition of the stowing task, where the goal is just to pick up everything and move it over here. This is sped up 15 times. So not quite that 400 picks per hour yet. Yep.
So what is the key differentiating factor between this entry and other entries?
You mean of the teams that participated this year in the challenge?
Yeah, I don't know much about
So I would like to say that the key factor was that we are like more clever and we came up with a better system. But that's a vast simplification. It's not just that we are just clever now. There were a few things, right? So the design of the gripper actually makes a significant difference, or how mechanically robust is and how much gripping force you can get while like still being robust against like overusing it, making collisions. And the second thing is integration, right? So to get this system to work well and to run fast, you need to spend time then like trimming down things and making sure that the output of the perception algorithm is compatible with the planner and the controller and everything, right? So having an initial perspective of how you're going to solve this problem, and then picking the answer to those 4 questions so that they're compatible with each other, it's also key. And we've been improving over time because we've participated 3 years, right? So that helped a little bit. That helped actually significantly. Perception algorithm using convolutional neural networks. Almost everyone was using convolutional neural networks. Small differences in the way we were using them. We were the only team that didn't retrain on site. Like the day of the competition, they were giving you 30 minutes with the objects of the competition so that you could gather new data and retrain your models. And we explicitly decided that we didn't want to do that, just to show that it was possible to grasp even without retraining for those particular objects. I think that helped in making sure that the system was well integrated ahead of time. I don't know. So you do that, and then everyone is happy, right? And we got first place in the stowing task, right? So not the entire challenge, just one of the tasks, one of the 2 tasks. So everyone is happy, but there are clear failure cases, right? And this happens all the time. Like this doesn't work all, like 100%. like one example here, one of the fingers falls right on top of an object and it just goes up, right? This is just normal. And it's not until here when we ask the question, oh, did it succeed or did it fail? Right? But while it was failing, which was a clear failure, it has no idea of what's going on. Second example, it picks up the object right at the edge, which is not great. And while it's going up, it still manages to keep it there, but you can see here that it's just barely a stable grasp, right? So the moment this goes up with high acceleration, it's just going to drop the object. But it doesn't know anything about it, right? While it was going up and it was seeing that the object was starting to slip, maybe there's something that the system should have done about it. But right now, no system can handle that. The reactivity that is necessary to be able to interpret the dynamics, the real-time dynamics of contact while we're grasping objects. So all that is good, but just summarizing, planning is based on visibly accessible grasps, right? So whatever we cannot directly see that something is accessible, we cannot pick it. And control is based on open loop executions, right? So I plan, I close my eyes and execute, and then I ask the question of whether it worked or it didn't. So if we look at how humans do it, and this is a cheap version of motivating the talk, but it's still effective, right? If you want to pick up this pizza box, right, where is the open loop execution and the visibly accessible grasp of this pizza box that I can trigger to get it, right? There's none, right? There's no accessible grasp of this pizza box. Somehow I need to put my finger under this, or wedge my finger under here and hope that I can get it, which is probably not going to be an open loop task because like there's going to be a lot of random noise as I'm squeezing there. So there's going to be some replanning involved in that. So there's some like spirally motion of the fingers as it's going down, and finally, first it picks up the lid of the box, which it didn't like. Oh no, yeah, wait a second, it's going up, so I'm just going to continue, and it works. Right, so this difference between grasp and grasping, right, between thinking about grasping as a static condition or thinking about grasping as a process, right, or as a reactive process, it's sort of like what drives my my interest in the problem and what I think that we haven't figured out yet how to solve, how to think or how to plan for those grasping motions. So how does this look like in the context of a real human grasp? So imagine you have a book in a shelf. What time is it, by the way? Okay. Are we also finishing at Berkeley time or no? At 5? Okay, so I need to speed up a little bit. So how does this look in the context of a human grasp? There's a book on a shelf, and I need to pick it. Again, there's no visibly accessible grasps here, right? I cannot squeeze my finger in there. So very naturally for us, we just put our hand on the side of the book, and magically, right? So I apply force orthogonal to the book so that I can pull it outside, right? So who would think about that, right? So I need to pull the book in my direction, for which I need to apply force in the orthogonal direction. But we do it anyway. We use the entire palm. We pull it down, and then we put the thumb here so that there's a more controlled pulling motion. And then in a swift motion, I just put my thumb on the other side and bump. Now I have the grasp that I wanted, right? But this entire process is something that it has to be planned for, right? I need to make sure that I understand that I can pull the book, I understand the implications of putting my thumb here, and I understand that my thumb is fast enough to go to the other side before the book falls. So how do we get the robots to do this? Big spoiler, I don't know, but here are some things that I believe are essential to move in that direction. The first one is being able to plan or being able to understand contacts that are enhanced, so to speak. So contacts that are not just the classical point contacts that we use in geometric grasp planning. So the palm is using an entire face contact, and at the same time is using the face contact of the wall of the shelf to be able to track this motion. So having a thumb, it's great. We can do opposable grasps, but at the same time, it also allows us to get it out of the way so that we also have a palm, right? Being able to have a gripper that is able to do palmar manipulation and at the same time prehensile manipulation in the same gripper, that would be fantastic. So on both on the hardware side and on the modeling side, it would be great to master that. Rich friction dynamics, right? So these kind of motions involve a lot of slipping, right? If I wanted to do this just by sticking contacts where nothing slips, it would be very clunky. So being able to master slipping at the same time that we also exploit sticking would be great. Reactiveness, right? So many of these motions are very noisy, and it's very difficult, or I think it's hopeless to try to have models that are very accurate. So a layer of reactiveness is necessary, being able to replan maybe. And finally, tactile sensing. A lot of the action that is happening during this motion is very difficult to observe visually, like the small amount of slipping between the hand and the book, right? Is the book slipping on my hand, or is the book coming outside with my hand? You can see it with your eyes, but it's probably too late already, right? So being able to use tactile information there in the control loop, it's essential. Okay, so by the way, these points are changing over time, right? Every time I give this talk, these are slightly different. So if you have any intuition, any ideas, any comments about things that are missing here, or things that you would change here, you would phrase differently, I'd be more than happy to talk about. Okay, so how do we get robots to do this? Now is where the second part of the talk comes, where I tell you we're working on these problems, and I want to show you a little bit of the kinds of things that we do. But before that, any questions? No need to? Just making sure. All right. So the first problem that research problem that I'm going to talk about involves in hand manipulation, right? So this is a classical problem in industrial manipulation. You need to pick up an object, and maybe we have some sort of affordance-based predictor of where to put the fingers, and we go to grasp it successfully. But then it turns out that to use the object, this is not the right grasp, right? We need to have the object like this. So having a small amount of in-hand manipulation capability, even with simple grippers like the kinds that we have in industry, would be very useful. And we've been looking into the idea of using the environment. Some of you might have seen this video already. This is sort of a video that Nikhil, the student that is working on this problem, cooked up manually. This is all manually programmed a couple years ago, just as a motivation to show that the robot can do these things, right? It can use rolling to get the right grasp. And it can push against a flat face to change slightly the grasp. And it can pivot the object very accurately and very fast, right? This is like 1/10x. So how do we get there? How do we get the robot to understand the mechanics of those processes and plan for these motions autonomously? Okay, so we want a planner that respects friction, respects at the very least our basic understanding of how we model contact in robotics. So respect Coulomb friction and respect principle of maximal dissipation, and respect like the fact that rigid objects are rigid and that there's no penetration, so that if it wants to move the gripper from here to here, it understands that if it does a straight push over here, the object is going to fall slightly, because Coulomb friction says that if there's a sliding motion in this direction, friction has to be opposed to the sliding motion. So there's not enough friction in the vertical direction to sustain gravity, so it will fall down. So the planner knows that and figures out to compensate for that. If the only thing we tell the planner is what is the coefficient of friction of everything, the geometries of all the objects, and the goal of the initial grasp and the final grasp. We want a planner that, as much as possible, it will do continuous pushes, right? So just for efficiency, if it has to change this graph from this grasp to this one, it will do in one continuous push, like in this case. And we want a planner that, whenever it's necessary, it can also concatenate different pushes to change the grasp on a more complex object. Like in this case, first there's one push, and then a second one down to do the regrasp. Okay, how do we do this? Well, the idea is to combine a low-level optimization-based model of the contact dynamics to account for all those facts, like Coulomb friction and maximal dissipation and rigidity of rigid objects. Combine it with a high-level RRT-based sampling planner that can incorporate the discreteness of jumping from one pusher to the second pusher. And finally, this is what the minimum you need to have a planner that can come up with those regrasps. As I'll show in a second, this will give you a very slow planner. Then you have to look for tricks to make it faster. So if you just do like standard linear complementarity formulations for contact, you can come up with these regrasps, but it takes in the order of hundreds of or tens of thousands of seconds to get to those regrasps, right? If you want accuracy. It turns out that there are easier ways that you can give up a little bit of the dexterity that you would have with the full problem formulation, just by imposing that every time that the object is moving, at least one of the contacts is sticking. The other ones can be slipping, but one of the contacts has to be sticking. This is analogous to stable pushing in non-prehensile manipulation, if you're familiar with, from Kevin Lynch. If you put that condition with the same complementarity formulation, you bring the times down to just a few seconds, and you can reduce it. This is a more recent work using motion cones to model that, to pre-compute stable pushing directions where you can plan for these things in less than half a second. So we've been working on formulating the mechanics for a while, validating them with experiments, planning for sequences of external pushes, and doing it fast and faster in current work. This is all Nikhil's work. And now we're starting to work with Delta and Lenovo. They are two automators that are interested in trying to bring these to assembly lines. Any questions? No? Okay. So second problem, also related to contact. We're saying using tactile information is essential. I think it's essential to be able to track the pose of the object while you're manipulating it, so that then you can be reactive about it. And if you just constrain yourself to use vision, you have intrinsic limitations, right? So there are going to be occlusions, and there's going to be low accuracy that you won't be able to, that won't allow you to do accurate in hand manipulation. So we've been looking into the problem of how to fuse tactile and vision information in real time. This is inspired by work from estimation community, the SLAM community, on coming up with fast ways to integrate constraints from different observation models or from different models that are guiding the interaction. So the basic idea is that if you just use a cheap camera to detect where the object is, you may get a certain amount of noise, but the moment you make contact, and this is an abstract version of a manipulation problem, right? So these are just like 2-point contacts so that we can think about where the constraints happen, right? The moment you make contact, you know that the object cannot be in penetration, right? And it cannot be in separation, it has to be in contact right there. So that adds a constraint to your estimation problem that hopefully you can use in real time to get a better estimate of where the object is. And that with a certain horizon, even if there's an occlusion, hopefully you can track the position of the object. Contact only gives you local information, so that's information that over time is going to degrade, but you might be able to use it for some time. This is just an illustration. So the basic idea of the experiment we've been working on is we get ground truth with a beacon system, right? So we know precisely where things are. And we get ground truth with force torque sensors here of the forces at the interaction. And then we have a cheap or a cheaper camera, webcam, that uses the April tag to get a noisy estimate of where the object is. And we want to, there you go, noisy vision, contact location, and pusher motion. And we know the action that the robot is doing. And we want to integrate these 3 sources of information in real time. So the output is the pose of the object. And as I was saying before, the challenges is like noise in the observation, occlusions, outliers, for example, in the estimation of maybe the April tag. I don't know if you've ever worked with them. It gives you a pose of the object which is like 90 degrees rotated. So you want to smooth those events, right? Okay, so we use techniques from the SLAM community that integrate these constraints very fast by keeping track of the covariances between the noise in each one of the constraints in real time so that we can integrate all these measurements. And once you do that, you can recover the pose of the object at about 100 hertz. And here's just like a couple illustrative examples of things you get. There's an occlusion here. And while blue is the last estimate from the webcam, red is the real-time estimate from the filter, right? So, and we can track in real time where the object is. Similarly, you can get more accurate estimates simply because you know where contact is happening. So while blue is the estimate from the webcam, red is outside from contact as it's reported from by the filter, right? So these are a couple things that you get when, or that you can possibly benefit from if we were to integrate tactile sensing or contact sensing in the state estimators. This is some error metrics from a vision baseline using ISAM, which keeps track of history of measurements. And instead of doing like a filtering scheme like EKF, it just smooths out the trajectory of the object over a certain history of observations. Okay, so this is sort of the story of how we've got here, right? So we started looking at the offline problem of recovering both pose and shape of an object as you're pushing it, right? So these are reconstruction of the shape of objects just from tactile interactions, traces of tactile interactions, basically the same technique. But the problem is that this only works in simulation. The moment you try to do it with real data, where the noise that is coming from real data, this degenerate too much. So this is sort of the motivation that led us to do or to investigate all do the experimental work on planar pushing and the data sets, if you've seen them. And after that, with a better idea of the models of the noise and the dynamics, we went to online with real experiments, which is what I just showed before. And now we're looking into to move into 3D problems, like for assembly, for example, where we want to integrate force torque sensings with noisy information from vision to get a better estimate of where the object is to do an assembly. But recovering it in real time so we can use this to guide the assembly. Okay. This work from Peter Yu, who is close to finishing, probably this semester. And finally, sort of to close the loop, I thought I would throw a few slides here about the work we're doing on like trying to, how are we going to bring some of these techniques to a real problem, right? Like picking up an object out of a bin. Part of the problem is that we don't have the necessary tactile feedback that we could use, hopefully, to feed those estimators. So we've been working on integrating tactile sensors at the end of the fingers of the grippers we're using for grasping. And this is a refactorization of sensors, type of sensor that has been developed, that was developed many years ago called gel-side, where there's an elastic membrane here, a polymer that deforms under contact, and there's a camera here that looks at the reflection of a mirror. And by looking at the changes in the deflection of this membrane, we can get some intuition about what is touching here. So gel-side, it's the original gel-side is kind of bulky, and we've been working on how we can refactor the optical flow and the illumination into the sensor so that we get it to be in a functional form. This is how it looks, the current prototype. This is the sensor. This is the sensorized part. And it's just a short video of the kind of feedback that you get. You can see here. We've been working on a couple things. One is refactoring the form so that it fits within these fingertips. But second, also working on the ruggedness of the sensor, on the robustness of the sensor. So gel-side, because it's a polymer, it wears over time, especially if it's under like when you want to do like a sliding experiment, right? If it's just pressure, it's more durable. But if you want to do this kind of rubbing motions, it wears out fast. So we've been working on re-engineering the materials for durability with a small price that you have to pay on resolution. Think of it as a low-pass filter. And at the same time, adding also a piece of cloth on it, which again works as a low-pass filter, but increases significantly the durability of the sensor. We've gone from being able to do a couple hundred grasps before like the sensor like wears out to do thousands of grasps, which I think it's still not enough. We have to go farther than that, but it's something. So the texture that you see here, it's actually coming from the texture that you'll see in a second. It's coming from the cloth, right? So you lose some of the resolution that you had on the accuracy of the shape of the object that is in contact. The texture actually is useful for detecting slip also. So it gives you markers to keep track of if things are moving or not. Anyway, so these are like example images of what you get. How do we make the robot react in real time? By using that tactile feedback. We don't know, but our robots are working on it, right? So we're sort of like embracing the learning approach, and we've sort of been working on developing this infrastructure so that the robot can stay overnight moving things from side to side and gathering these tactile signatures of what it feels to successfully pick up objects or unsuccessfully do it. And sort of moving in that direction. Elliot working on the hardware, and Francois and Maria working on the control loop. All right, and that's all I have. Have any questions?